hope it is visible.
Yes, it is.
Okay, so can I start?
Yeah, go ahead.
Okay. So, hello everyone. So, today I'll present the paper Time-LLM published at ICLR 2024. And the goal of this talk is to build intuition step by step, starting from the basic, like the time series data concepts, and gradually moving like how LLMs, like large language models, can be used for forecasting. So let us start it. So this is like the overview that we are going to discuss today. So I will begin with briefly reviewing like what is time series data like and why forecasting is challenging. Then I'll motivate like why large language models are relevant here. After that, we'll walk through some like the architecture, experimental setup, results, limitations, and the final takeaways. So let us start with the time series data. So we'll we'll understand like for basic thing like what is time series data. So a time series is a sequence of observations collected over time where the order of data points matters. Mathematically, we can represent it like this, which is a simple representation. And the examples include like electricity consumption, traffic flow data, CPU usage logs, or EEG signals. Like EEG, we have discussed like in this talk so much. So they are also like related to time series. So unlike tabular data, shuffling a time series destroys its meaning because the order matters in the time series data. So, like, what are the key characteristics of time series data? So, the most real world time series are composed of several overlapping components. So, these include like long term trends, repeating seasonal patterns, and random noise. As you can see in the diagram, also, like the data, the trend is like over decreasing or increasing, seasonality is like repeated patterns, noise is like some spike or something. So another key challenge is like long-term dependency. Events far in the past can influence future values, and this makes modeling time series fundamentally harder than the static data. So like these are some challenges as well. So what is the time series forecasting? So, the time series forecasting means predicting future values given historical observations. So, here the T denotes like the length of observed history, and H is like forecasting horizon. Like, horizon is just like the next time steps which we are going to predict. So, the problem here is as the horizon grows, the uncertainty increases. Patterns become more complex and errors accumulate. And this is why the long horizon forecasting is particularly challenging. And this difficulty is exactly where the strong sequence models become useful. So here in the diagram, I've tried to show like how input goes to prediction model and it just give the output for the future timestamps. So this is how the forecasting works. So now we'll see some traditional approaches for time series forecasting. So classical approaches like ARIMA rely a strong assumption on linearity and stationarity. So ARIMA is like very like standard statistical model, which is like a traditional model autoregressive integrated moving average prediction model which uses like which is really good for the linear data but not really good for the non-linear ones because it does not work well for that. And now the deep learning models like LSTMs and transformers, we know like they are like good enough, but they need like large label data like data set because transformer need more training Like the most models are like task specific and they don't generalize well across data sets. So this motivates like looking for more general sequence models, right? So this raises a natural question. Can we reuse knowledge from large pre-trained models? So let's move on to the next part, which is LLM. So, why consider large language models? So, large language models have shown remarkable abilities in sequence modeling that we all know and long range dependency learning. They excel at attention based reasoning over the long context. However, LLMs are trained on text tokens. We know that, right? But the time series data, it is continuous and numeric. So the issue is related to the representation mismatch that that time LM aims to address. So the challenge becomes like how can we represent the time series data so LLMs can understand it better, or we can utilize the strength of the LLMs. So let us quickly take the core question of time LLM, this architecture. So, the central question of this paper is very simple but really powerful. Like, can we use a frozen large language model for time series forecasting? And the constraint is that LLM parameters must remain unchanged, and only small additional component will be allowed to like train. So I know it may be hard, but this would be more general and the model would be more efficient. So this was the target for their like model. So now the core idea of this time LLM. So the key insight is that we know that the LLMs are language models and they are general sequence reasoning models. Language is a sequence of tokens, and the time series is about like numeric thing, right? But what they are doing is that time LLM like converts the time series data into token like representations and feed them into a frozen LLM. And this process, they are calling it as reprogramming. So, as you can see in the diagram, they are transforming the input in such a way that is understandable, like in the word form for the LLM, and they are keeping the backbone like frozen. LLM backbone is frozen, and we are getting the output, and they are mapping out the output according to the desired target domain. It may be time series forecasting, it may be something else, maybe like anomaly detection, some classification task. So it depends like on the use case. So this is the core idea. We'll discuss how this works out and like what exactly the architecture is. So this is the high level overview I'm giving. I'll discuss each point like in the next coming slides. So like how it is working is like the time series is normalized. We split it into the patches, like we divide it into different patches and they are embedded, and the patch embeddings are reprogrammed using the text prototypes. We'll discuss what is text prototype, and prompt prefixes are added along with the patch prototypes, and they are all going to the frozen LLMs, and then the outputs are projected to forecast. So only here the lightweight input and the output layers are getting trained. So the main body remains frozen. So let us understand the input representation. So they are not working on multivariate data. They have tested with like the univariate data sets. So like univariate is like just single variable. So each series is processed independently, and the steps, as we discussed, is like normalization, patching, and then embedding. And this produces a sequence of patch embeddings that can be further processed. So let us understand from step one, which is time series series patching. So we start with a univariate time series, which is like XPI, which we are denoting it by this. So I is the index of the like series, and T is like the number of time steps over here. So instead of feeding this long sequence directly into the model, Time LLM splits it into smaller segments, and we call it as patches. And after patching, the series becomes a matrix like XP of I, as we are denoting it, and P is representing the number of patches, and LP is the length of patches. So P cross LP over here, and now there is a formula over here like the number of patches created. So T minus LP upon S plus 2, where here the S is like the stride. Stride is like step size, and LP, as we discussed, the length of the patch. And we are adding it here too. You may be wondering why. So it just for boundaries. So first and the last, they are making sure they are also added, like they are not skipped anywhere. So the number of patches is like T minus LP upon S plus 2. So this is very important because it converts the time series into compact sequence of tokens, and the diagram is just a visual representation how it is working, like simple patching. Now the second step is patch embeddings. So until this step everything is like purely numeric. So we take any queries. Okay. So we take each patch and map that into the vector space using a linear layer. So so far we have not used any LLM. We are just simply trying to make sure the data is like very well structured, like we are dividing into patches, and then we are getting the patch embeddings after using this linear projection. So we got XP cap over here, and like it's just that we prepare the data so it can be aligned later. So now the main component comes like where their novelty comes into the picture. So patch reprogramming. So we'll start it like this, like language models we know that trained on the text embeddings, and the patch embeddings what we are getting now, they are very numeric and like coming from the time series data. So now if we feed like these numeric embeddings directly into the LLMs, it will not like interpret, and it will not be meaningful for LLM really well because just numeric, right? So Time LLM solve this by using this reprogramming technique. So idea is not to change the language model at all, not even the training or something, but it is to like change how the input looks like to the language model. So specifically, Time LLM aligns the time series patches with language embedding space using cross attention. So they use the cross attention mechanism over here. So like the language model has pre-trained word embedding matrix usually, which is E here denoted by E, and V cross D. So V is the vocabulary size, and the D is the dimension of the LLM which they are taking. And however, like if we take this whole like embedding space, this would be very large because I'm telling this is related to a LLM. So it will not be efficient. So rather than using it, they use another technique, which you can see in the diagram. There is a linear probing, which means like applying a linear projection to the frozen LLM embeddings to select the text prototypes. So text prototypes are also like the embeddings, but they are kind of a representation like in a smaller way. So we are decreasing the vocabulary size. So V dash cross D, dimension remains the same. So V dash is like much smaller than V. So we are decreasing the vocabulary size over here. So, and these prototypes are like a common subset of language concepts. They like such as related to time series data. So would be like up, down, steady, short term, long term, etc. And these prototypes acts as a semantic anchors that connects the time series pattern to the language models, because like the language concepts and the language models like understand more this, right? So at this point, like the cross attention is usually here is to connect the patches and the prototypes, and each time series patch embeddings is working as a query. So query would be the patch embedding, and key and value would be this e dash, which we are getting like from the text prototype. So these text prototypes would be like our query and the value pairs. And cross attention computes like how relevant each text prototype is for each batch, and it assigns higher weights to language concepts that match like the local time series pattern, and then it combines these concepts into the new representation. So the output of this step is a new set of fetch embedding, which is not at all numeric, and these embeddings are live inside the language model's pre-trained embedding space. And this alignment is crucial because it allows the frozen LLM to process time series data as if it were a familiar sequence. We activate the LLM's pre-trained reasoning ability without updating any of these parameters, right? So this is how this reprogramming is working out. Now we are done with the reprogramming. Now it comes to the key design choice of the LLMs, like how the language models, without breaking the numerical precision, we are giving the input like context also. So we'll see how they are doing it. So instead of converting the time series value into text, LLM uses prompt as prefix. And this means like we add the textual information before numeric tokens rather than asking the language model to generate numbers as text. So here I have added a snippet like how they are giving the context. This is related to electricity related data. So they are giving some domain, some instruction, some in statistics. So, and then at the end, they will add their embeddings, right? So the data context tell like what kind of signal it is, like where, like, is it related to electricity, load, etc. The task instructions specifies like what transformation is required and like what needs to be predicted or something. Input stats means like mean, standard deviation, like it is just making sure that the like more information we are trying to give to model so that it can perform better, like overall trend, lags, etc., in a numeric manner. And mathematically we are just concatenating the prompt and the z, which is like the output from the previous step, like the z, which we are getting like the reprogram patch embeddings, and the prompt, which is having these informations, and then at the end we are feeding it to the LLM, which is like the frozen backbone, and we are getting the edge. Now the last step is the output projection. So like this is the fifth step. So we are getting the output from the backbone, and we first discard the prompt tokens because it includes the prompt tokens as well, and keep only the output representation like corresponding to the time series patches. And these representation are then flattened and pass through a simple linear projection layer, and this projection maps the LLM hidden states to the final forecasting output. And like forecasting is regression kind of task, so accordingly we do it, and it gives the timestamps, it predicts the timestamps, and we get y, which is like the output over here. And together with patch embeddings and reprogramming layer, it is the only one of the only component that are like updated during the training, and all parameters of the language model like are not getting trained. So we are just training these output weights, like output projection layer, and the input weights like that we were discussing in the reprogramming layer. So this design keeps the model efficient while still leveraging the LLM's sequence reasoning capabilities. So will like I just want to give you the complete overview also, like how like we discussed each part, but how the integrated one. So we'll quickly recap the complete time LLM pipeline, how it works. So we start from the raw univariate time series, which is first normalized for stability. And in step one, we can see here like we are normalizing the instance normalizing, then we do patching, like the one number you can see in the image, and then we get the output. And then we have the step 2, in which each patch is embedded into like the fixed dimensional vector, and then we have a reprogramming layer. So patch embeddings are reprogrammed using cross attention with the language model's pre-trained embedding space that we discussed, like the text prototypes and like multi-head attention, and we get the final reprogrammed patch embeddings. Step 4, we apply the prompt as prefix. So we somehow combine the first, we add the prompt, and then we add the reprogrammed patch embeddings, and then the entire sequence is processed by this blue region, like the pre-trained LLM, frozen LLM. In step 5, we discard the prompt tokens and project the LLM outputs to like the linear projection, and we get the time series forecast. So crucially throughout this pipeline, the language model itself is never fine-tuned. Only the lightweight components, the patch embeddings, the reprogramming layer, and the output projection are trained. This allows Time LLM to reuse powerful pre-trained reasoning while remaining efficient and stable. With this overview, we can now focus like how this approach performs well on data sets. So like the experimental setup. So this is the experimental setup. So the model is evaluated on standard long horizon forecasting benchmarks. So, like ETT, these are like well known data sets related to time series data, electricity, traffic, weather, and ETT is also related to electricity. So, these are like these all were tested for like this architecture, and performance is measured using the MSE and MEE. So as we know that the goal was the forecasting, so they calculated the error between the predicted and the actual thing, so like mean square error and mean absolute error. Baseline include some like patch TST, dlinear, times net, GPT-4TS. These all are like time LLM. They are all well known like architectures for time series analysis. So So they just make sure a fair and the comprehensive comparison with the standard baseline and the existing architectures as well. So now quickly take a look at the results, how they got. So the table one is representing the results for long-term forecasting. So here they are saying like the all results are average for four different forecasting horizons. So here H horizons means like the times, because this data usually be in hours. So 24 is like 24 hours, 36 like 36 hours. So 24 hours is just like it is predicting for 24 hours. And then 36 like 2 days, 3 days, 4 days, and similarly. Here we have, we can see like in the data, just don't want to go deeper into the table, but we just try to understand like the lower is better here because this is error. So the red ones are like the best performing. So time LLM is performing best out of all. So this is the main key observation. So the observation is like the time LLM is competitive and better across different data sets, and like there are different data sets, and these are the architectures. So in columns you can see different architectures and different ETTH1, ETTH2. These are different data sets, and this important thing is that this performance is achieved without fine tuning the LLM. And now, like, we'll interpret the results like what they tell us. So this is another result table which is like related to zero shot learning. So in the prompt, they didn't give any example, so they just did the zero shot thing. So here also their architecture performed really well and it got lowest error. So these results validate the core hypothesis of the paper, and reprogrammed LLMs work well for time series data that we understood, and these are like specially effective for long horizon forecasting and low data regimes. And this suggests that LLMs can act as a general purpose sequence models. And now, what are the limitations? So, these are some limitations. So, reprogramming is linear. So, this is one main limitation over here. Second is like the patch design is heuristic. And third would be that forecasting horizon is also constrained by the LLM's context length. So it depends on like the context length of the LLM. So this may be another limitation for this architecture. And limited interpretability. So as we have seen like the linear prototypes, so they have not emphasized much about the prototype. So there is a need of more interpretation over there. So these are like important direction for the future works as well. And they can also integrate the multi-model thing here. Like right now we're just having one aspect, so along with the text and some images and other things. So now we'll come on to the conclusions. So the time LLM reframes the time series forecasting as a sequence reasoning problem, and it introduces the input space reprogramming and effectively leverages the frozen LLMs. This approach is efficient, scalable, and also generalized. The key takeaway is that LLMs are not just language models, they are powerful reasoning models as well, like sequence reasoning models. And now, these are the key references which you can refer later. And thank you very much. If you have any queries, please let me know.
I have a few questions.
Yeah,
Thanks for the good presentation.
yeah,
Can you go to the architecture diagram that you showed?
yeah, of course.
Yeah,
Yeah.
so here
Mm.
you mentioned we are like on the right
Mm.
bottom corner,
Yeah, yeah.
the time series data.
Mm-hmm.
Since the LLMs have trouble understanding continuous
Mm.
sequence data, we are doing patch embedding and also like
Yeah.
some word embeddings as linear prototypes.
Mm.
Uh, my understanding is that we are teaching LLMs to understand this time variation as within each patch. If the data goes up, then let's say that it understands as a text up.
Yeah,
Like, does it
yeah.
understand
Yeah.
the time series based on the take words describing the trend, or does it understand the continuous time series data? My knowledge is in this is limited, so I'm just curious.
Okay. So your point is really good, like how it is like understanding the data, which is true. Like so, the thing is what they are doing. Uh, I'll go with the second step. Yeah. So here they have like the time series patches, like the data, which is the numerical data, right? The second is they are making sure that we know that the numerical data, the LLMs cannot perform really well with the numerical data, and previous like works show that really well. So what they did, they took another component which is like pre-trained word embeddings, like the large corpus of the data like which we have for LLM, like the knowledge. And then they did a linear probing, which is like the linear projection, and they get the text prototypes. And here this part is getting trained. So based on the forecasting loss, it is getting updated, and we are getting the better representation of the data, like in terms of the text. So these text prototypes would be some words which are related to time series data. It may be up, down, or like, something related to
Mhm.
the time series data. And we are making sure they are aligning with the time series patches via this
Mhm.
multi-head attention. So
Okay.
we are querying the patches, like we are giving the query patches would be the query, and the key value would be that embedding space, and we are getting the aligning ones with the patches. So here somehow what they are doing, they are combining the time series patches, the data, with that words, right?
Mhm.
And
Okay.
at the end they are getting a reprogrammed patch embeddings, which are like the better representation of the data. So they are, in place of changing the large language model, they are keeping it frozen. They are changing the way they are giving the input.
Okay.
So,
Okay.
yeah, they are making
The
sure, yeah, the input is better, like so that LLM can understand it.
Okay, and like the
Yeah.
patch embedder block, like what
Ah,
exactly does it do? Like it takes the
embedder,
time
patch
series
embedder
data.
is just also a linear layer. So we know that we have patches which is in the numerical thing, so it just converted it into vectors, so
Okay,
that
okay.
like for better,
We
like
train
we,
the patch embedder as well, right?
yeah,
Like
yeah, it's just a
the
linear layer, and we just, yeah, we are training the weights in that. So weights are getting trained. So here, this symbol, the fire symbol, these parts are getting trained.
okay.
So the output
Somehow
projection,
this patch embedder tries to project the
yeah,
patch time series data into the same vector space as the
yeah,
text
yeah,
prototypes, right?
yeah, yeah, exactly.
Okay, and in the text prototypes, do let's say if it is in
Mm-hmm.
the list I saw, like it's the words are describing the trend, like up, down, steady,
Mm-hmm.
decreasing, something like that. But let's say,
Mm-hmm.
does it include any information about the data? Like let's say if it's electricity data, do we include word electricity and power usage or that kind of words also into the
Oh, yeah,
word?
that's interesting point. So for that, here the patch embedding, reprogramming part, that is not taking care of it. So the part which I'm discussing here, so the embedder, can you see on the left hand side, we are
Mhm.
having pre-trained LLM embedder. So here we give the data set description that you are saying, like domain, instruction, input statistics. So domain
On the
include
frozen one,
that,
right? Like left
yeah.
bottom.
Mhm. N-
Okay.
Not, but at the end, we are giving both of these to the pre-trained LLM. So LLM is aware of the context and also the data. So
Mhm.
we are giving it as like prompt as prefix. So in prompt, we are giving this description. So this is one of the example, like they have used this kind of
Mhm.
description for their data set because they use the ETT data. So
Mhm.
that is electricity. So they give some information like electricity consumption and instruction and stats related to that.
Okay. So this
Yeah.
prompt is what, like in my understanding,
Hmm.
like it makes use of the knowledge of LLM
Yeah,
instead of
yeah,
just
yeah,
trying
yeah,
to
yeah.
regress over the time
It's
series.
just for like better understanding of the data, like make giving some context to LLM.
Yeah. Thank- Yeah. Thanks. Thanks.
Yeah, thank you.
Thanks, Aditi. Thanks for a wonderful presentation here.
Thank
Uh,
you.
I have a very quick questions.
Yeah, please go
Okay.
ahead.
Yeah, it was very detailed, and I just downloaded this paper and now and I'm just going through that paper. So
Yeah,
that is good. So when we say fixed frozen LLM,
yeah,
so that's a pre-trained LLM, right?
yeah, exactly. Pre-trained
So
LLM.
do we have a mention of what kind of architect of that was? How much was that? What kind of training it had in the paper?
Okay. Okay, yeah. So, can you see this main architecture? So, this is the genuine pre-trained, like the main one we are discussing, right? So, they have used GPT-2 and Llama, these two architectures, like these two language models they have used. So, I don't think there would be any specific like training for that, like the genuine GPT-2 and the Llama model they have used.
Okay, okay,
Yeah,
okay,
so they have mentioned the models which they are using in the
okay.
pre-trained architecture.
And okay, and
Yeah,
just can you
yeah.
explain a little bit differently what is patch in this? What are we considering as a patch?
Yeah, so patch is a small section of time series data. So let's assume like the time series data, it's very like long time series, the timestamps. So what we are doing, we are dividing it into like, let me show with
Patches.
this. Yeah. So the time series data is like this, as you can see. So we divide it into different parts, and these small sections they are called as patches.
Hmm. And that's kind of a window of time
Yeah,
series, say,
yeah, yeah, similar concept. Yeah.
a similar
So
concept.
this is like one of the paper, like patch TST is another paper which came earlier than this, and they use this idea of patching. So later on they use just the same idea in their time LLM architecture.
Okay.
Yeah.
Um, and when we say patch, then
Mm-hmm.
what we are saying is that we are um, every time, let's say there is a patch of 5 days, so
Mm-hmm.
5 day time series, but then the next time series is from second day to sixth day, and the third time series is to from third to seventh. Is that what I understand?
Mm,
Yeah,
yeah.
I
So
think I think that will depend on the stride. So
yeah,
if your
that's right.
stride is one, that means that you're just going from first to the second day for your five window.
Mm,
But if your stride is greater than that, like it's equal to
Okay.
the size of your window, then it becomes
Okay, that
separate.
the stride then
mm.
okay determines
Stride
how
makes
I'm sliding this window.
exactly, like there may be like overlapping slides. So if it is like less than like the stride is like two or one, so it depends like will there be overlapping or not.
And
the
what
time.
are we taking? How do I understand what is the y values for this? I mean, y hat kind of predicted values. So, for example, I have a patch of 5 days. So,
Mm.
how many we are predicting for that patch?
So in that you need to fix, right? Like as we discussed in the data outputs. So here they did for 24 hours. So the data for 24 hours, the data for 36, 48, and the 60. So
Mm-hmm.
yeah, so that's the output would be the prediction, obviously the regression task, the numeric values. So it will depend like what we are fixing over here. Right, in the like while we
Okay.
are coding we
Okay.
can make sure like how many of these we actually need,
Okay.
Mhm.
Yeah,
you know.
just last question, Aditi.
Mm-hmm. Yeah.
Really good effort from your end.
Yeah.
Just one last question.
Yeah.
So I understand this is a univariant
Mm.
time series
Yeah.
which they have taken, right?
Yeah,
So
exactly.
have they mentioned anything about any future something which we can do as for
Yeah, for
multivariate analysis?
future work, yeah, exactly. Your point is exactly, it is right. So they have mentioned the limitation like that I told. These are few limitation, and along with that, the multimodality and multivariate testing, they all are like future work. So we can look for that, obviously.
Okay. So do you
Yeah.
think
Mm-hmm.
just for a discussion or
Mm-hmm.
open for everyone to answer that,
Mm-hmm.
how can we actually go for a multivariate on from the time from the LLMs?
Okay. So like we are working on the multimodality aspect of it. So like we are trying to make sure the time series data, the time patches which they had. So along with that, we are making sure we are giving the text input and we are giving it in the prompt. But for the multivariate thing, I think procedure would be similar, but would be there's I think there I'm not very sure about it, but there would be changes in the like dimensions and the matrix size. Like it would be like a bit
Yeah,
complex. Yeah,
yeah.
because
I
it
think the
would
most
be like
Complex.
Okay,
yeah.
the
can you
most
go back to the
Mm-hmm.
sorry, yeah. Go ahead, Moj.
Mm-hmm.
I was saying if we want to use this in a multivariate time series,
Mm-hmm.
I think
Yeah.
the most challenging part will be patching.
Mm-hmm. Yeah, exactly.
So patching may basically I think they are taking the
Mm-hmm.
mean of each patch, right, to represent a
Mm-hmm.
single data point.
Yeah.
And if you take a mean, column-wise mean of the univariate time series, then it can actually change the entire meaning of the time series.
Yeah, and the
So I think
aspect like the stats and everything will this will change and yeah, would be complex a
Wait,
little.
wait, wait. You're talking about univariate, right? I don't think they're taking a mean of
Mm,
the patch. So I think you have a patch of sequence of values, and that goes into so you have patches of, let's say,
idea I think
4,
would
and
be
then it
same.
goes.
Yeah.
So
Yeah.
just for this paper, I'm saying that they are just passing the patches through a linear projection layer and converting them into some fixed dimension instead of taking
Yeah.
a mean of anything.
Yeah. There is no mean of patch. They are not taking that. Like I'm talking about this here, the mean and the aspects here in the stats. So they are giving that information here in the prompt.
Hmm.
in that case, I think if you have a multivariate time series, so
Hmm.
mm,
Yeah, the simplest thing that I could think of is
Hmm.
just do the exact same
Multiple
process
times.
for multiple times, and
Multiple
you get
times.
an output representation for each
Hmm.
of your time series, and then attach a
Hmm.
classification or a regression head on top of
Hmm.
it of all
That
the
would
representations that you get.
that would be simplest approach. Multiple times doing the same.
Arath, can you come again?
So if, for example, in this image, if you see, you have a green uh, green vector that's coming out of the pre-trained LLM just before the output projection. So for each of the time series that you have, you generate this vector similarly.
Mm-hmm.
So you get like 5 or 10 or however many projections you want of different
Mm-hmm. Yeah, yeah,
multivariate series, and
exactly.
then the output projection would be applied on top of all of them. It would be
Mm.
expensive to train because you'll have a
Mm.
different patch reprogramming and other things for each of the multivariate series.
Exactly. Like future work may be like improving. Yeah, this is a good idea. Like doing it multiple times, so it would be efficient way like for doing this. Yeah. Yeah. That's one approach. Good one.
So I had one question. So basically, after we reprogram the patch embeddings,
Mm-hmm.
so I think the
Mm.
if you look at the maximum,
Mm.
like patch wise maximum attention weight corresponding to a particular token, right?
Yeah.
So if you like combine all the patches and their corresponding maximum attention tokens, like what is the what basically what language does it look like? I think it will be a gibberish, right? Something like that. So do they mention something like related to that? What exactly are the token representations, like the maximum attention score token representations of the patches?
I didn't see like anything like really like mentioning about this thing. That looks interesting. Like what is the like represented like these patch embeddings? They would be numerical vectors for sure, but not very sure about.
Can you like go back? I think
Mm-hmm.
you had maybe explained this concept.
Uh-huh. Mm, This uh, this one
Yeah,
or
this one. Okay, so the patch one in this example is coming from steady and long, two words like right some
mm-hmm.
and time late, I don't
This is
know.
just
So
an example. Yeah.
yeah, this is just an example, but I think if you combine all of these words,
Mm-hmm.
maybe just pick one word corresponding to a single patch, which is
Mm-hmm.
a maximum attention score, it will be gibberish, right? It will not make any sense. So
Hmm.
don't you think like this is like a not very useful way to model
Efficient.
because
Huh. Okay.
you're basically are passing some gibberish words to the model and expecting a prediction of the time series forecasting.
Mm,
So I think
yeah.
like this doesn't make sense. Like, mm, but yeah,
Mm,
maybe this
But
works. I don't know.
yeah, it works, and like somehow it is helping like to understand, right? Like even if we give the simple words, it may be more efficient, but we are giving in the text form, which is like for LLM it is better
So
Yeah,
rather
maybe
Aditi,
than.
unnecessarily.
Mm-hmm.
have they done any ablation on the
Mm-hmm.
patch size?
Patch size.
Yeah. What patch size did they select, and have they given any details or ablation results on that?
No, did for the reprogramming layer, like if they remove reprogramming, what it does, and something like that. Not exactly the patch size.
Hmm. Might be in the appendix. So.
Maybe in the appendix, yeah. In the main results, they do not.
कहाँ पे publish हुआ है paper?
ICLR
Uh,
2024.
So if it's in ICLR, I believe that they should have this
They should have.
patch
Maybe in
size.
the appendix, yeah, of
Yeah.
course.
I think that if you have a very long patch size, you may lose the
Hmm.
basically you may exploit the time series. But if
Yeah,
you
of
have a very
course.
small, then you basically are not doing any advantage of patching.
Hmm.
So it will be
Hmm.
somewhere in the middle.
Hmm. Hmm. Yeah.
Hmm.
Hmm. Batch size is like actually it makes a lot of sense because in time series the data like is related, order matters a lot. So yeah, there should be something.
Hmm. And have they mentioned about
Mm-hmm.
how much data, like an ablation of the on the percentage of data used to train this?
Yeah, yeah. Okay, so not exactly that, but they did ablation studies like they did a few shot forecasting also. So along like the zero shot one, right? So like they take the 10% of the data in the prompt and they got the results, then 20%, then
No, you would
5%.
still have to retrain train your reprogram patch embeddings in the output layer, right? You'll still
Mm,
have to train that. I'm asking about how much data do you need to
mm.
train both of these layers that you are training? Have they given
So
any data on that, like how much data they have used to train that for any task?
no, I don't think so. Like there is no ablation study for that, but there should be some fixed data that they are using for that.
Mm,
I'll look over that once, yeah.
mm,
If they mention it in somewhere, like an appendix or somewhere, the data size.
Acha,
But
one
they,
thing, like,
mm-hmm,
did they try something like without this reprogramming, just
mm-hmm.
passing the patch as it is to the LLM, and we can just fix the LLM, as you said, no fine tuning, and just fine tune, obviously train an output layer and an input layer. So I think that will also work if we have an LLM.
Yeah, they have shown the results, but it is not better than this one.
अच्छा कौन
Huh.
से रिजल्ट्स हैं?
uh,
Mm, there is a table, I think table number 5 or something.
5.
Just let me tell you. Mm. So the table number 6, so they show ablation study for a particular data ETT1. So reprogramming, if they do
Okay.
patch as prefix, if they do like data set context. So like for each part, as you
Hmm.
said, and default is like the default one.
So Llama
uh,
performs it.
which
Yeah,
which
Llama
which
and
table
G.
is this?
Table number 6 in the paper, page number
Hmm.
9. Yeah.
Mm-hmm.
So they tested two architectures, Llama and GPT-2.
Mean square error है, okay.
Han mean squared.
Mhm.
They have done some kind of a reprogramming interpretation too. Wow.
Yeah, there is an interpretation, like not mentioned because it is very brief, but yeah, there is some.
हाँ इसमें होगा like what words are
Hmm.
picked or what tokens are
Hmm.
picked corresponding to each time series data.
Heat maps and stuff. Visualization.
Nice.
They have also provided the code.
Yeah, the code
Yeah.
GitHub is there.
If it's ICLR, they have to provide code. You
Hmm.
can't publish without code in ICLR.
अच्छा
The code is there, like and
the
I have
Chinese paper
tested
है.
it is completely working. So
Hmm.
yeah.
Yeah, it's a Chinese paper, right? Chinese
Hmm.
paper are ऐसी टाइप की बनाते हैं वो लोग, कुछ अलग से ढूंढ ढांड के बना बनो के कुछ पब्लिश करते हैं.
Hmm.
Mm.
Hmm.
नोटिस किया है मैंने ये.
Yeah, like IBM research and universities like अलग अलग Alibaba group, काफी लोगों का contribution है.
इंटरेस्टिंग आइडिया तो
Very.
इंटरेस्टिंग है.
Idea is really interesting. Like what we all think is like we do something with LLM. They think something different. Like what if we change the representation?
नाइस.
It's a bit weird to do this
Yeah,
because
हाँ.
of course.
कोई चाइना ऐसे ही करता है भाई.
because you are just
Yeah,
you're attaching the reprogrammed patch embeddings
yeah,
इसको वो linear layer लगा के
हाँ,
inside of the LLM at some
yeah,
place.
yeah, exactly.
Because in the LLM you don't even know
Yeah,
how do you separate an embedder and a body.
yeah,
All of the
exactly.
layers are the same. You cannot
Mm,
call one as the embedding, the other
mm,
as the
yeah,
body. So
yeah,
you also have to decide which part of the LLM you will call as embedder.
yeah, yeah, exactly. It's a bit. Idea is very interesting and also like how they are doing it. And that's working out. It's something great.
So
Like
Aditi,
to
the
look over.
text prototypes are also
Mm-hmm.
in the embedding space of the same
Mm.
pre-trained LLM. Is it the same embedding space for
Yeah,
text?
yeah.
So for example, let's say the
Mm.
embedder had 5 layers. So the
Mm.
text text prototypes which are being used will also be created from the five embedding layers?
Can you repeat like the first
Ca-
part?
Can you
Mm-hmm.
go to your reprogram patch embedding slide?
Mm-hmm. Yeah.
So here I'm saying
Mm.
that okay, first you have a pre-trained word embeddings. The
Mm.
pre-trained word embeddings, does that mean that you are using the initial word embeddings, or you are using the transformed word embeddings that you get after five layers of your trained LLM?
No, I don't think this is like the original LLM, like the word embedding space the LLM is having. So like the huge corpus, the E, right? And then we are somehow getting the, like, loss we are getting. So we are improving the text prototypes which we are getting after the linear probing. So text prototype are just like representation, like we chose initially something, and then based on the forecasting loss it is getting improved, and weights it's
See,
a linear.
if they are the initial word embeddings, then
Mm-hmm.
okay, go back to your complete
Yeah.
model slide.
Yeah.
So, so, so
Ha-
in the pre-trained LLM, let's
mm,
imagine that we had like
mm.
10 layers,
Yeah,
right? In the
we should
pre-trained
have.
LLM embedder, just the embedder part, you had 10 layers.
Mm,
Now,
mm,
in the patch reprogramming, you are using just the first layer to transform the do all of these reprogram patch embeddings, and then you whatever you get, you are attaching it to the in this after the five layers of the LLM. So
mm.
isn't
Okay.
that kind of a mismatch? Yeah.
Uh, I don't think there should be, like, because I think patch embedders, they must be, they are making sure that the embedding which they are getting from the pre-trained LLM on the left side, they should match with the patch embedder embeddings and the linear pre-trained word embeddings, right? So it should match, and then only it will go to the LLM, right? So if there would be mismatch, how it will work
So
out?
the mismatch I'm talking about is just the
Uh-huh.
number of layers being used. So in the
Okay.
pre-trained LLM, you'll be using five or six layers,
Mm-hmm.
and
Mm-hmm.
in the patch reprogramming, where
If
you
you use
have a
less. Mm-hmm.
you'll just be using the first layer of to get the pre-trained word embeddings and transforming it in some way,
Mm-hmm.
and
Mm-hmm.
then attaching it to the LLM.
There may be then. Yeah, of course. I didn't think about that aspect. Yeah.
It will be like
Hmm.
approximating all of
Yeah,
these
of
five
course.
layers with just
And
one
with
layer.
just one layer. Yeah, exactly. Yeah, there might be some problem there, of course.
Hmm.
They have not mentioned this aspect well.
Hmm.
Good point.
Okay, anybody else has a question?
मैं ये नोट कर रहा था
Mm-hmm.
कि all of the evaluation studies they have published for this ETTH, right? So I think it's
Mm.
just this data set is for temperature. I think like they predict temperature, right, of a
Electricity
transformer.
and temperature, yeah.
So temperature, if you are predicting, I think it's in degree centigrade, and if you're off by zero point 0.3 or zero point 0.4, it doesn't really matter, right? And all of
Mm-hmm.
these MSCs, MAE are in the ranges of zero point 0.3 to zero point 0.4. So if you are basically you want to basically
Mm-hmm.
think of this as a deployment perspective, from a deployment
Mm-hmm.
perspective, I think the stakeholders will always agree if you are off by zero point 0.4 and that architecture is basically smaller or maybe easier to deploy compared to an architecture which uses batch programming and whose error is zero point 0.3
Mm-hmm.
zero point 0.3 degrees centigrade. So they will always prefer the former, right? They will never actually ask us to deploy the latter model, which is using all of these complexities to reduce
Mm-hmm.
the error only by a very
Hmm.
small margin.
Mm-hmm.
That is true.
So So I think
हम्म,
like इन्होंने थोड़ा गुमराह करने की कोशिश करी है
थोड़ा सा।
people को।
हाँ, there are some other data sets also like weather और
the
कुछ
the
टेस्ट तो
best
किए
part
हैं।
the best
हम्म।
part of this is that it is a general purpose thing. Like
Yeah, it's a general purpose, so we can use
it's
it
not
for other use
specialized.
case. Yeah, for forecasting in place of like if we change this output projection, that thing, right? So we can either use it for classification, we can use it for some other like related to time series data. We can make sure for different use cases. So
हम्म।
I think it will not limit the idea. So idea is great. So that's
So
why maybe
so
yeah, yeah.
output projection
Mm-hmm.
में so is it like you are predicting just the class or just
Yeah, it
whatever?
may be the classification. So what we are
So
doing,
you
we
you
are
are not
doing the
you are not
classification.
doing like
Hmm.
in LLMs you are generating words and stuff, right?
No,
You're not
no,
generating, you're just predicting.
predicting the thing. Yeah.
Okay.
हाँ वो आउटपुट है तो जैसे टाइम सीरीज का ही निकलेगा
Ah,
आउटपुट तो।
ha, ha.
Hmm.
There is a prediction. So it may be a classification problem as well if we change the
So
output. Yeah. Yeah.
like
they
language
haven't talked about, right? What will happen if you start predicting from this, like generating from this?
No, no, no.
हाँ मैं वही
That's
पूछ
not.
रहा था पता है कि इसमें ऑटो रिग्रेसिव कैसे होगा।
Yes,
No.
ऑटो रिग्रेसिव इसमें लगा के देखो तो सही हो क्या रहा है?
वो generation
What
था।
are you
नहीं
getting
वैसे
as
कर
output?
सकते हैं एक तरह से बट
कर
हाँ
सकते हैं।
पैच कैसे होगा वो तो एक ही आउटपुट निकलेगा एक बार में
हम्म।
उसको पैच कैसे करोगे।
नहीं, even if you patch everything and you have given everything all at once
हम्म।
and you ask the model to मतलब कि हाँ भैया हाँ देखो
Generate.
देखो, कुछ भी जनरेट करके दो, even if it's just language, you have given it a task of classifying or regression or anything and it's generating
हम्म।
it. So
हम्म।
what if we just ask to generate auto regressively? हमने उसको
Yeah.
रिप्रेजेंटेशन बीच में एक बार लगा दी, वो एज इट इज चलती रहेगी उसमें.
वो
Yeah.
घुमाता रहेगा वो zoom कर करके और सेम आउटपुट निकलेगा फिर तो घुमा एक ही चीज घुमाएगा तो।
पता नहीं, we can try.
Yeah, it would be
Yeah, it
interesting to
would be
see.
interesting. Yeah, of
So what
course.
do you get as output if
Output.
you do auto
हम्म।
regression to this
हम्म।
पूरा?
मे भी इतना अच्छा ना हो क्योंकि GPT-2 जो इन्होंने अभी यूज किया है वो तो बहुत
Yeah,
अच्छा नहीं
using
है तो।
using
अरे बहुत बढ़िया है।
GPT-2's choice is just is
Yeah,
great.
it's a
भाई जीपीटी टू
bad
बहुत
like
बढ़िया मॉडल है भाई। बहुत तगड़ा
GPT-2.
मॉडल है। मेरा फेवरेट मॉडल है जीपीटी टू।
Okay.
Because you have trained it.
ना ना सारे उसी पे भेज ना भाई।
Hmm.
जितने भी स्टेट ऑफ द आर्ट मॉडल आ रहे हैं जीपीटी टू पे
हाँ.
लगे हुए हैं भाई।
हाँ, ये
उसको
तो है।
बड़ा उसको स्केल करे जा रहे हैं
हम्म।
और कुछ
बहुत
इनोवेशन निकल
लाइट
नहीं
वेट
रहा।
रहता है, हाँ ये तो है।